This video is part of a suite of short activities we have put together to celebrate SSERC's 60th anniversary. The number 60 is clearly significant here, so we've chosen to make it the focal point of the activities in these videos. First of all, we're going to have a look at neodymium, which has the atomic number 60. From a chemical point of view, there's not a great deal to talk about, but one feature of neodymium that a lot of people are aware of is that it can be used to make extremely strong magnets. And these magnets can be used to demonstrate some interesting effects. We are all familiar with normal magnetism, properly known as ferromagnetism, as it's most commonly associated with iron. There are other metals that will also display it though, to a lesser degree: nickel, cobalt, manganese, etc. There are, however, other forms of magnetism. Diamagnetism is the tendency that all materials have to weakly oppose an applied magnetic field or to repel a magnet, though in many materials other processes overcome it, so it's not observable. A classic example came a few years ago when Dutch scientists levitated a living frog using diamagnetism. There are no unpaired electrons in a diamagnetic material, and there is no permanent magnetic effect. Paramagnetism is due to the unpaired electrons and change in the alignment of the electron paths from the action of external magnetic fields. It is easy to demonstrate, as long as you have a strong enough magnet and a sensitive balance. Here, I place some solid nickel sulfate on a 3 decimal place balance. I'm standing it on a tall plastic universal bottle to raise it up, otherwise the strength of the magnetic field will directly affect the reading on the balance. The magnet is held in a clamp, and as I slide it across, very close to the surface of the nickel sulfate, you can see the reading on the balance changes. It actually decreases, as shown by the minus sign to the left, showing that the salt is being attracted to the magnetic field. Nickel salts are generally paramagnetic. This arises from the electronic configuration of the nickel 2+ ion, which has 2 unpaired electrons in its d orbitals. The strength of the effect can vary depending on the particular nickel salt and its crystal structure, as the surrounding ligands can influence the energy levels of the d orbitals. As well as demonstrating paramagnetism and diamagnetism, you can also use these magnets to look at the interaction between the magnetic field and the ions generated in electrolysis. Here I have placed a neodymium magnet beneath a tile with a petri dish on it, which contains sodium sulfate with some universal indicator in it. As you can see, when the electrodes are dipped into the solution, we get the expected purple at one electrode due to the formation of hydroxide ions, and red at the other from the formation of hydrogen ions. But as you can see, the interaction with the magnetic field causes these hydrogen and hydroxide ions to be repelled from the electrodes, and they experience a magnetic force at right angles to the motion. This causes a swirling pattern in the liquid that you can see. Whether this is of any significance for any chemistry curriculum, I'm not sure, but it is certainly an attractive and interesting phenomenon.